Now let's look at one-forms, which are basically designed to integrate over curves. So a one-form is going to be an expression of this form. So we often write them with the lowercase omega. And so it'll be an expression of this form, a of xy dx plus b of xy dy. And now a and b are going to be real or complex valued functions on some domain. And this dx and dy are just going to be placeholders for us for now, and they'll kind of tell us how to integrate the one form over a curve. And probably it's better to leave them mysterious for now, but we do allow kind of, we do perform basic algebra with them where you consider these kind of independent things. So if I add this, I can add two one forms, a dx plus b dy plus c dx plus d dy, where a, b, c, d are all just functions. Well, you would combine them as if they were variables. Okay, and our goal is to define integration of a one form along a curve in a manner similar to Riemann integration. So we'll use approximating sums and so forth to define what it means to integrate the one form over the curve. I do want to introduce the one forms that will most often be integrating in this course because it's a complex analysis course. So the one form dz will be defined to be dx plus I dy, and a 0,1 form will be a function times dz. So omega of this form, f of z times dz, will be called a 1,0 form. And the notation comes from a more general object that you may learn in several complex variables, but we don't have to get into it now. Maybe you just think of it as sort of a dz form, and it really is just a certain type of one form. If I write out f as u plus iv and just multiply it out, it's really just u dx minus v dy plus I times v dx plus u dy. And we can also form 0,1 forms, which involve dz bar, and its definition is here, dx minus I dy. And these would just be one forms of this type, f of z times dz bar. And every one form can be written as a 1,0 form and a 0,1 form, because if I have a dx plus b dy, then using the following handy formulas, I can turn dx into an expression involving dz and dz bar because of this formula, and dy into an expression involving dz and dz bar. And I won't go through all of it right now, but you would just put that in here, and I could express any usual one form in terms of a, so maybe I'd get a new function here and a new function here. So I could express the original one form just in terms of dz and dz bar. And as I said, we'll most often be looking at the 1,0 forms because we're going to be integrating analytic functions times dz. Okay, but how do we integrate these? Well, like I said, we have to do something like Riemann integration. So here's the setup. It's a little technical, just like all kind of Riemann integration setups. So let's say we have a curve, gamma, and we have a one form where the functions a and b need to be defined on the actual set formed by the curve. So gamma's image, gamma of the interval AB. And now to form what we call an approximating sum of this line integral, we need to form a partition of our interval, and we need to form a tagging of the partition. Let's see, so the partition is just a way of breaking up the interval into t0, t1, all the way up to tn, stopping at b, and then a tagging of the partition. So let's see, so I've got AB, and I've broken it up into pieces, T0, T1, T2, T3, T4. And then a tagging of the partition is just to choose a point in each one of these subintervals. So I'll have T1 star, T2 star, T3 star. I put it on the boundary, but that's allowed. T4 star. So I pick a point in each one of these intervals. And then, once you have all this set up, well, we need a little more notation just to make our approximating sums look a little more pleasant. So I take the points of the partition and plug them into gamma to get points along the actual curve, so zj, which I'll write out as xj plus iyj. And then I'll plug in the points of the tagging of the partition to get what you might call sample points in Riemann integration, zj star. And I'll have the change in z, so zj minus 1, which we break up into components of delta xj plus I delta yj. Now, this is all of the setup we need to write out our approximations to this integral we're trying to define. So an approximating sum to this line integral, it looks just like you would do a Riemann approximating sum, or Riemann sum. So I'll define it as S of omega, comma the partition, comma the tagging. So I need all this different data there. If I were smarter about this, maybe it should really be gamma of the partition and gamma of the tagging, so that it's points on the actual set on the curve. Okay, but then the approximating sum is just to form A of the sample point times the change in x plus B evaluated at the sample point times the change in y. And this is our approximating sum. I won't go too much into the motivation. That's something you learn in Calc 3, but these are usually motivated in Calc 3 as work integrals, where A and B would be components of a force, and computing this line integral would be like doing force times a tiny change in displacement, and you would add that up all along a curve to get work. That's not exactly what we're doing, although you can try to relate the concepts. I mean, it is what we're doing, but you have to sort of do extra work to really tie it to that situation. Okay, we're going to be interested in mostly integrating 1-0 forms, which will be of this type, f of z times dz. And these will have approximating sums of this form, f at the sample points times the change in the z's. And you would just get that straight from arithmetic by looking at the expression there. Okay, and finally, the last thing to introduce before we can actually give the definition of our line integral is we need to talk about partition refinements. And a partition Q of our interval AB is a refinement of P just if it has more points in it. So that's not a big deal. And we can always form a common refinement of two partitions by just taking their union. Okay, so now we have a curve, a one form, a way of approximating what we want to be this line integral. And so we'll say that the line integral exists if you can form kind of consistent approximations that tend towards something. So the line integral of omega along gamma exists if there's a number which will be the value of the line integral, such that you can that your approximations are eventually all as good as they need to be. So all of our approximations will be close to L. So there exists, or I should say, for every epsilon, there exists a partition of AB such that for all refinements of P, so if I throw in more points, and irregardless of the taggings of that refinement, so it doesn't matter about the sample points because our partition is so refined that the taggings don't influence our estimate too much, that we have that our approximation minus L is controlled, so it's less than epsilon. So we can always find a partition that throwing more points in won't change our approximations. So what you could do is choose a sequence of epsilons going to 0, and you find partitions that make your approximations get closer and closer to this L, and you could even make them refinements of each other, and you would tend to L in a consistent manner. And if you can do this, we declare that the line integral exists and its value is L, and we write it as integral over gamma of omega. Now, one of the nice things about this is, although it's technical, the definition is independent of equivalent parameterizations. So if I reparametrized gamma over here, I would be choosing my partition from a different interval, but I didn't use any of, sort of geometry of this interval. I'm just picking points of the interval, and then when we compute our approximating sums, we're just evaluating the functions at gamma of tj. So we're basically just taking a curve and breaking it up, or finding a whole bunch of points here that that are so kind of densely populated that when I compute these expressions like a delta x along here, that we get a consistent computation with all of these different approximations. And I'm not using anything about the parameterization other than basically that it gives me an ordering of the curve in the correct way. Okay, so the definition is independent of parameterizations, of equivalent ones. And if I do the reverse order, so integral of gamma, integral along gamma of omega is equal to the negative of integrating along the reverse of gamma, and that's just because the delta xj's and the delta yj's would sort of switch direction for the two different approximating sums. So you'd be doing everything in the reverse order, so you'd get a minus sign in front, and that matches how Riemann integrals are defined. Okay, so this is a very technical definition, but it's very nice because it's independent of parameterizations. Now we're going to give situations where we can compute these integrals easily, namely along C1 curves, and we're not going to refer back to this definition too much, but it is useful in sort of gaining some really fundamental knowledge about these integrals.